Okay, so you're back. I've not ran you off, hopefully, and you're here to maybe, hopefully, finish this stuff up as far as pieces and parts go, right? So in the last video, we talked about the dilution water and replacing it and when to replace it every day. And we also talked about the acid, the hydrochloric acid, that 1 molar concentration for our instrument, and how to make that sample or that solution or that acid, and when to replace it and when to make fresh and when to load it up on the machine, and then how to replace the flow line contents to get rid of all those air bubbles and to keep that tubing line flushed and clean at all times. So in this video, we're going to continue on and we're going to talk about another way that we can keep our system clean, and that is through the use of a filter. So there is a filter that can be changed on this instrument. This filter is going to be located near the end of the instrument, right before it gets to the detector, the NDIR detector for you. And there's a purpose in the filter, and you probably will understand the purpose of the filter without even watching this video. But I at least want to show you what this filter looks like, maybe give you a cost for the filter, and maybe at least hone in on the location, the exact location of this thing. So I'm going to bring up the schematic again. And in this schematic, if we kind of follow through toward the end of the instrument, there is a filter that is happening right here. And that filter is happening after the halogen scrubber. So you need to keep in mind the process. I have a sample. That sample got injected into the combustion tube. That sample was combusted and CO2 was generated. And then that CO2 is going into my dehumidifier, which is pulling out residual moisture. And then the CO2 is going through the halogen scrubber, which is pulling out halogens, because we talked about the bad things about those. And then before it goes into the NDIR, we are sending it through another filter. And this filter is really called a membrane filter. And this membrane filter is 0.5 micrometer pore size. That is super, super tiny, super, super small. All right, so what does pore size mean? Well, let's say that you have a piece of filter paper, and this maybe is a coffee filter, all right? In the coffee filter, I want you to think of it as a grid, all right? This is the easiest way to think about it. And that grid is divided up in sections. Well, a pore is basically the opening of one of those sections. And, you know, it doesn't take a lot of effort to put water in a coffee filter and see all of that water filter through the coffee filter at a very fast pace. That is a very good indication that this pore size is very large. So these openings or the holes that your solution is getting poured through, those holes are quite big, and it's not holding that liquid behind. Well, in a laboratory, as you can imagine, that coffee filter, maybe that pore size is not very good for us. It's not going to be removing everything that we need to remove. So we have filter paper that's a little bit better, and the reason that it's a little bit better is that the pore size is a little bit smaller. So it's going to take my liquid a little bit longer to go through, but that's okay because it is holding back a little bit more contaminant that I might not want in my filtered product in the very end. Okay, well, sometimes this normal filter paper is not good enough either, and we have what we call membrane filters. And these membrane filters, quite honestly, they don't even feel like paper. When you grab filter paper in our laboratory, it will be very rough, it will be very stiff most of the time, right? It will have this feeling of paper to you. But membrane filters are completely different. Membrane filters have super, super, super tiny little holes that are on the inside of this material. So only really pure water can go through, as well as very small compounds. And these compounds could be the traditional types of compounds that we are working with in a laboratory. Any type of bacteria, any type of large particulate will normally stay behind on the membrane filter, because those holes are so tiny that even something like bacteria can't make its way through, which is why we use it in a laboratory environment. All right, so the 0.5 micrometer pore size, that is about standard of the 0.45 micrometer that we use when we start filtering our samples before we put them onto the machine. So at the very end of this, what they're doing is that they are just making sure that your CO2 is just CO2 at this point, and that these larger kind of particulate pieces cannot make its way into the NDIR detector. So in this filter, and that's what you're seeing over here to the right-hand side, this is the kind of one hookup, the centerpiece here. So a tubing line will lead to that center, and then your sample will flow through the membrane filter, and you can kind of see it opaque, kind of whitish there, and then it goes out of the back end of the filter and then goes on to the NDIR detector here at the very end. This membrane filter, it's not very expensive. These things are about $45 a piece. They're quite large. Over time, it is a good idea to exchange this filter out. Just as with any consumable piece, over a series of years or months or number of samples that you're running, this thing can get a little dirty, this thing can get a little wonky, and it's a very easy replacement. You just take the side piece cover off of the instrument, you take the cover off. This is one of the pieces that's kind of up front and center. You just unsnap the front, unsnap the back, put your new filter in, and then snap the tubing lines back on the front side and the back side of the filter yet again. That's all that you have to do. But the important thing here is that this filter prevents larger particles from going into this NDIR detector. So that way your NDIR detector, which is a lot of money, doesn't get messed up over the course of a few months or a few years. That is just extra protection that the instrument and that the manufacturer is giving you to ensure that that's not going to happen on you. All right, so if you're going to be doing maintenance on the inside of this thing, or if you have a routine maintenance schedule, this is not a pain. It's just a few screws that you've got to loosen up. You take the side cover off, you exchange the filter, and you put the side cover back on. No big deal after that. So finally, the next piece that I want to talk about is this carbon dioxide absorber, the CO2 absorber. They put this on here because they want to be environmental friendly, okay? All right, so where is the CO2 absorber? If I take a look at the schematic, the CO2 absorber is here at the very end, and this is where everything basically ends up. So here's the story with the CO2 absorber. You, as a person, blow out carbon dioxide all day, every day, okay? We breathe. We breathe in O2, we breathe out CO2, and that's kind of the food source that many plants will need in order to grow and get bigger and produce fruit and vegetable and everything else. CO2 is part of that process. Well, the issue is that this machine generates CO2, and this CO2 was a concern for some people. And there was a regulation that was put in place, and because this machine is generating CO2, carbon dioxide, again, you're breathing it out, this machine's breathing it out, they believed that they should have a CO2 absorber on that machine just to absorb all of the extra CO2 that this machine might be producing. Give me a break, people. I'm going to bring in 2 or 3 extra people into a laboratory room and tell them to breathe. They're going to be making more CO2 than this instrument is going to be making. All right? So don't get me started with the CO2 absorber. It is on the machine. It is part of the schematic. It's part of the flow diagram. And guess what? It is part of what you need to be replacing. So this TOC instrument normally has the CO2 absorber at the very top. And this is what you're seeing in the picture. You can see the label on the front. The label on the front says CO2 absorber, and there's two lines that basically come into the CO2 absorber. These are lines, of course, that are leading out from the NDIR detector, because everything kind of flows through and out, and then the sample goes into the CO2 absorber. These crystals, they're chunks on the inside. Those crystals absorb all the carbon dioxide that's getting produced, and then just normal, clean air, I guess you could say, will leave this bottle and it goes out of the exhaust of the machine. So that's the purpose of the CO2 absorber. It is a consumable that has to be replaced. It is something that you want to replace on a routine basis. And believe it or not, there's no indicator on these crystals either. So that means that you're just going to have to kind of trust it. You're going to have to kind of look at what kind of samples that you're running, kind of get a good idea of how much CO2 is getting absorbed, and how long these crystals can actually last you as an individual. And then you put a routine maintenance in place where you can begin to exchange this bottle. Exchanging the bottle is very easy. You normally do not unscrew the cap here. The entire bottle gets replaced. So these tubing lines up at the top will be disconnected from the bottle, and then this entire thing will be trashed and you will order a new one. So because they are so concerned with CO2 production from this instrument, you now are being very wasteful, and you're throwing away the crystals that are on the inside, and you're also throwing away all of the plastic that this bottle and this lid and everything else is made in. All right, so again, give me a break. Don't whine about your CO2, and because that you did, now we have to go through extra hoops, extra measures, extra money just to replace this simple little CO2 absorber. The CO2 absorber, again, the concern here is you're generating greenhouse gas. In the laboratory, CO2, you can't have it, right? This is poison for everybody. All right, so that's why this CO2 absorber had to be installed. On the inside of this bottle, there's something called soda lime. That is the name that it goes by. And soda lime, the soda, kind of think of sodium, all right? And normally it is sodium hydroxide that gets added into here. And then you also are going to find a calcium hydroxide. So it is a mixture of two hydroxide crystals. And these are absorbent crystals. That basically means that it will absorb the CO2 that's getting pumped out of this machine. It latches onto it and it keeps it. So over time, the calcium hydroxide and sodium hydroxide crystals are going to get used up. They're spent. There's no more active crystals on the inside of that container, and that container has to be replaced because of that. All right. In parentheses, I've also put potassium. Potassium is another option for people to use. So instead of sodium hydroxide, you might find potassium hydroxide getting mixed with calcium hydroxide. And that, once again, is also called soda lime. But sodium is typically going to be the go-to element of the two. There is a video of replacing the CO2 absorber. I'll show you that in just a second, but the replacement cost here is $70. So every couple of months, maybe 3 months or so, this CO2 absorber is going to have to get removed. I'm going to have to trash it all, be very wasteful, and then I'm going to have to spend more money, $70, to put a new CO2 absorber on the machine and allow it to absorb more of the carbon dioxide that my samples are producing. Again, it's just a regulation thing. That is just part of the machine. That's just the way that it is, and we have to kind of follow suit because of that. So that is why you're seeing that in the schematic, and that is where it's located, and now you kind of know where that's located. So the CO2 has to go through the detector, and once the detector sees it, once it measures it, where does that CO2 go? that CO2 goes to an absorber. So that bottle absorbs all of the carbon dioxide that you're producing over a course of time, and then that bottle will have to be replaced again on a periodic maintenance schedule. So this is a video of them replacing the CO2 absorber. You're seeing them take the lines off of the top. That entire bottle with lid gets trashed. Again, very wasteful. The new one comes in, you take off the caps, and then you hook the tubing lines back up to the bottle. All right, again, one tubing line is coming from the detector and the other tubing line is leaving the bottle and going out of the machine. So that's why there's an entry point, if you want to think of it that way, and an exit point. If you didn't have that exit point and that second tube was not there, this bottle would continue to get air and CO2. And over time, of course, pressure would build up and it would explode the bottle. So we have to have an entry line and we also have an exit line. And that is the purpose of those two hookups at the very top. So again, it's just a simple, let's unplug them up here at the very top and let's replace the bottle. That's all there is to it, folks. And that is the story of the carbon dioxide absorber, or the CO2 absorber. Okay. Finally, one more thing that I want to point out is the ready status. The ready status, we've talked about a lot of pieces and parts here, right? We've talked about the syringe, we've talked about an 8-point valve, we've talked about temperature, we've talked about flow rate, we've talked about NDIR stabilization, we've talked about baseline, we've talked about quite a few things, and this instrument will constantly measure all of these values for you. And if any one of these are off, then this machine will not run any sample at all. So the ready status is going to be green. Green's ready to go. I'm ready to run sample. That's what I want to see, green. When it's running sample, it goes blue, okay? So blue is for run, and green is going to mean ready. All right. So with that said, there is a box on the software. This is what it looks like. And there's a couple of check marks on this box. If I go through and look at this tab, the tab up here at the top is TOC. That's my TOC analyzer. That's the main one that has all the pieces and parts in it. It looks like there's an NDIR section, and it also looks like there's a temperature section. Okay, so if I look at this a little bit closer, it says baseline positive, and it says okay. Then it says baseline fluctuation, and it says okay. And then it says baseline noise, and it says okay. All three of those are in reference to what the NDIR is seeing. So the NDIR needs to be very stable, which means a pretty flat line needs to be there if no sample is running through it. So if I'm not running sample and I'm starting to see a little bit of this that comes through the NDIR detector, then I know that there's a contamination issue. So the machine is going to let me know this, there's a problem and you need to fix it. And I need to fix that problem and turn the machine back on, and hopefully I can get rid of all of this noisy kind of baseline that begins to happen. So the positive, the fluctuation, and the noise is really all related to that particular type of line. All right. Also notice on the screen here, there's negatives. Here's a negative 100, and then there's a 200 to 400 to 600 to 800 and 1,000. Normally what we want to see is a baseline that is going to happen at the 0 mark. We want it close to 0, and we want it to stabilize near 0, give or take a little bit, okay? We do not want to see an elevated baseline. If we see an elevated baseline, let's say it does get stable, but it stabilizes right up here above 200 and it goes flat, we know that there's another problem. That other problem is probably a detector problem, an NDIR problem. So the signal here is a 200 for our Shimatsu. If it's lower than 200 in signal, which is millivolt, then that machine will be okay. It will not like the elevated baseline, but it's okay with it. And it will let you run samples, and you can still get data, and you can still record. However, over time, the NDIR could start to decompose if you're not keeping a routine maintenance schedule on it, if you're letting your halogen scrubber or your filter go bad, if something is causing a problem and it's starting to corrode the NDIR, then you're going to see a higher than normal millivolt signal. And when this goes over 200, it could be a very bad sign. So you would have to readjust the baseline. You would double check your NDIR, and you would readjust the baseline to get it back down to 0 whenever possible. Okay, so that's the issue with the detector, and that could be an error code that you're going to get bad, where it says you're never ready, you're never ready, you're never ready. One of these boxes will be bad. X, you can't do anything at all, and that could simply be due to the fact that you have an elevated baseline in your detector, and it needs to be reset, or it needs to be fine-tuned, or you need a whole new detector in order for this thing to work. Okay, down here at the bottom, it says temperature, and it says furnace, okay, and it says 680 degrees. The software does constantly measure the temperature of that furnace, and it wants it stable, and it doesn't want it to change very much. If it does begin to fluctuate, if it never reaches 680, or if it cannot stay at 680, you're going to get a red box here, and that is a furnace problem that you might have to call Shimatsu to have them come down and take a look at. The dehumidifier is also going to be looked at as well. This dehumidifier has a temperature. That temperature has to stay constant. And the NDIR also has a temperature that has to stay constant. What you're seeing on the screen right now, it says 50 degrees. So that NDIR detector is in a what I would call container, or an area that is contained and insulated. So we want to make sure that that temperature does not fluctuate. We want to make sure that it stays at that temperature from here on out. And again, if there's a issue with the detector as far as the temperature goes, you're going to see a red X here, and it's not going to let you run any sample at all, period. Carrier gas flow. Carrier gas flow is also going to be measured. Right now, this box says 150, and that's normally where ours is as well. And then the supply gas pressure. Remember, we talked about the gas tank, which is air, and that air has an intake system. And I can't pump out too much at one time. That was the purpose of the regulator. And I told you on the software screen, there is a number, and that number is 200. And I want to make sure that I am within plus or minus 10 of that value. Well, there is the pressure. There's the system setting that it wants. So if it begins to look at this pressure that's incoming, and if it goes lower than 190, or if it goes greater than 210, then this could give me an error that's associated with the machine, and it will not run any sample at all, period. Finally, the next thing is down here at the bottom, and this is called the sparge gas flow. So what you need to think of here is, in that syringe on the side, you had an airline, right? So how much air is coming in to bubble that sample? That is the sparging gas. So that sparging gas should also be set. And if that sparging gas cannot meet and stay at 100 mils a minute, then this machine is going to kick back an error, and it's going to say that there's a problem. Sometimes that could be a piece of crimped tubing. Sometimes that could be a bigger problem. But this air intake is also getting measured at all times, and it's getting recorded, and the machine is going to be looking for that as well. So this is what we call the background monitor. This is actually staying active at all times that the machine is on and operating and running. And if any of these settings go haywire, then the machine is not going to let me do squat with it. I cannot bypass those errors. I cannot get the machine to run a sample, even though that one of these come back with an X. I have to fix that problem before I can run the machine. So that's just the way it is. That's part of the software. That's part of the oversight that goes on. And quite honestly, it's also part of the safety protocols that are in a laboratory. The last thing that they want is to hire someone to come in and run TOC samples, have a problem with the machine, not want to fix it, and then continue to run samples on the machine just because they know how to bypass those features. So good luck getting data, and good luck getting the correct data if that's what you decide to do. So these settings and these protocols are in there to stop you when there's a major problem. So the flow rates are constantly measured, the temperatures are constantly measured, and the detector is constantly double checked to make sure that it's all working the proper way. All right, so that's where this video is going to stop. We've got one more. And in that last video, I want to tell you a little bit about this industry in more detail, and I want to tell you a little bit more about the options or the choices that you have for a TOC instrument. Again, I'm only going to focus on Shimadzu because that's the instrument that you're going to see with us. That's the instrument that we have in our lab. But these pieces and parts and other attachments, they can come along with any manufacturer, not just Shimadzu. So we're going to walk through some of those different options that are out there on the market. I'm going to tell you some differences in them, why one would be better than the other, and so forth. And that way you'll have a better understanding of the TOC field and all of the alternatives that are out there for you to choose from. So come back. We've got about one more video. That's it. That's it. Don't you feel good when I say that?